Okay, in the previous two discussions, we examined the position time graph, and we found out that the slope of the position time graph give you the average velocity. And the second lesson, we went over the velocity time graph. And this time, there are two significance that we can find from the graph. One of which is the slope gives us the acceleration, and the area under the curve or under your graph is just the displacement of the object. So we proceed with the third one. The third one is acceleration. So by definition, acceleration is a change in velocity. Okay, and it is the rate of change of the velocity against time. So therefore, you can write it out as A. We use the symbol A for acceleration. Change in velocity over delta t, or just the elapsed time. So you have Vf minus Vi, and this is just Tf minus Ti. So again, in our case, we'll just be talking about average acceleration. So because the form of the acceleration, instantaneous acceleration, is the differential of the velocity against time. But again, we can just use this basic definition. And if you can see here, the important quantity there, that there must be a change in velocity. So I can't emphasize that one more, that acceleration is change in velocity all over time. So automatically, if there's no change in velocity, your acceleration is zero. Okay, so it's a common mistake by students that they will just think of acceleration as just velocity against time, but it should be taken into consideration that you have delta V there as in the definition. And if you're gonna look at the signs, or at least the units of your acceleration is meters per second squared. And the thing about the direction of your acceleration, if you can see here, the only quantity that is vector quantity here is the change in velocity. So the direction of acceleration can be taken note that direction of acceleration is the same as the change in velocity. Again, it's given by delta V. Okay, I just want to emphasize that we're talking about a vector quantity. That's why I placed an arrow on top. So the direction of your acceleration would be the same. It should be the same with the delta V. Okay, so whatever is the direction of your change in velocity, that would be also the direction of your acceleration. So it's not equivalent to the direction of your velocity. Remember that it has a different definition. The change in velocity is not the same thing as the velocity, because change in velocity is a quantity that involves the final and the initial velocities. Okay, so acceleration can be positive, speeding up, or negative, slowing down. So acceleration is a vector quantity. So it is a vector quantity, so it has direction. So again, where is the direction of your acceleration? It's equivalent to the change in velocity. And later on, if we're going to talk about dynamics, I also mentioned this one last time, that the direction of your acceleration is actually the same thing as the direction of your net force. Okay, so remember that since acceleration is a vector quantity, it has also direction, but it doesn't mean that the acceleration would have the same direction with your velocity or the final velocity. Okay, what is the same with your acceleration is the direction of the change in velocity. So if if a particular object is accelerating, if you can see in this position of the object against time, if you can see, so the distance increases. So that are just small dots there. Okay, because if you have noticed, if the velocity is constant, we have equal amount or equal distances between the dots here. So in this particular case, if you can see, in this particular, you can, this is a particular motion of an object. So it increases in distance against time. So if you're gonna graph this one, this is what you will get. So if you can see increasing position against time. So the graph would be something like this. So it's not a straight line. So if it is not a straight line, right away you can say that the object is accelerating. Well, in this particular case, actually increasing in velocity. Because remember that the velocity of the object at any time t is given by the tangent lines at any point here. If you can see, the tangent lines here increases. So that means that the velocity increases. And if you're going to graph this particular motion with the velocity against time, so remember that in the second one, this is velocity. So velocity against time. So you'll get a straight line. So there's a uniform increase in the velocity. And when that happens, if you can see, you get a straight line in your acceleration time graph. So if you can see here, a straight horizontal line of acceleration will give you a sloping upward. Okay, sloping upward. So straight here, this becomes a straight sloping up. So you have a fixed velocity. The change in velocity against time is constant. Remember that a straight horizontal line tells you that the acceleration is constant. But if you can see in the position time graph, this is not straight. So it's changing. The position increases in, well, the magnitude is distance, if you can see here. So it increases against time. So if we're gonna check another motion of an object, if you can see here, it starts from here, and then, so if you can see the distance it traveled, it decreases. Again, the distance of this motion diagram is that given by this one here. If you can see, it decreases. So the distance decreases. If you're going to graph the motion, the position against time graph of the motion of this particle here or this object here, you'll get this particular graph. If you can see, it is something like this. And you can verify that one. Again, the slope, or at least the instantaneous velocity of the position time graph, is given by the tangent lines. And if you're going to create tangent lines here, if you can see, the slope of the tangent line decreases. Okay, it decreases. So you would think of that, if you're going to interpret that one to the velocity time graph, if you can see here, it's decreasing in magnitude. Okay, until maybe if it reaches, it stops here, so the velocity is 0. And if you can see, the acceleration is negative. Okay, So if you're gonna go from here to there, if you have a negative acceleration, you should expect that the line would look like this in the velocity time graph, and the position time graph, depending again if it started at the bottom or what, it should be something like this.